Hi, everybody. So I'll be talking about enhanced SYCL offloading support to use the new offloading model. And most of the people working on this project are listed in this contributors site. It's Arvind, Maxim, Nick, Alexi, and Mike. And so I'll start off on the agenda with the overview of the SYCL offloading and highlight some of the important features. Then talk about the proposed design to use a new offloading model. Yeah, it's sort of, when we say new offloading model, actually in the community, they've been using this offloading model for some time, and that's the default model they're using. We just refer to it as a new offloading model because we are right now migrating to that. Then I'm going to talk about what are the deviations from the existing community flow that we need to make, and what are the reasons why we made all this, and what are our plans for trying to address some of them. And then I'll talk about the work we have done so far and what we're planning to do next. Okay, so SYCL offloading is basically, SYCL is designed for data parallelism and heterogeneous computing. It sort of provides a consistent programming model with based on the C++ and API, so that you can program for CPUs, GPUs, FPGAs, and AI accelerators. And the compiler, I think, enables multiple tools, and so generally it involves at least one compilation for the host, and then one compilation for each target specified. So let's look at how you would invoke the compiler. So you have clang and then you say fsycl. That means you want to compile where the program contains cycles. And then you want to also compile for some targets, and so you would specify that using the -fsycl targets, and you can provide multiple targets. Here I'm given an example where you can say Intel GPU YYY and XXX. So I'm trying to hide the names. I'm not sure what names we can export, so just use generic names, and then you provide the test file. And then here's how the program looks like for a simple program, but you may find some incorrect things in this. But the point I'm trying to do is illustrate how it looks, a simple SYCL program. So on the top, you have what you call the global data, the dev-var, which exists both on the device and on the host. And then you have a function where you pass in the queue to the function. And then you use the queue to update the value on the device. So you do a queue, using the queue, you do a copy, and then you wait for the thing to be completed. And then you would do the kernel submission, which is highlighted in yellow, to submit it to do some sort of summation of the indices into the, I think, variable which exists on the device. And so this is sort of the SYCL kernel. The general gist of it is that this is the highlighted yellow thing is the SYCL kernel. Okay, so how does the offloading work with SYCL, and what are supported? So SYCL in general, the way we do, SYCL can be compiled to provide ahead of time PTX code or AMD HSA code. But for Intel, we always generate SPIRV, and this SPIRV, you can embed this into the host object file, and then it'll be jittered. So JIT is just-in-time compilation, where you would invoke backend compiler when you're running the program. Or you can also do AOT, where it's, you can pre-compile it during compile time using the backend compiler and generate the device binaries for Intel GPUs or FPGAs or OpenCL CPUs. So here's the overview of the SYCL compiler using the new offloading model. So let's talk about I'm going to talk about the compilation phase first, and then I'll talk about the linking phase. So you have a SYCL program here, and basically you invoke Clang on the SYCL program. So what's this is going to be is like a two-pass compilation. In one of the passes, we generate the host object file. In the second pass, where we are targeting for the device, we generate the device IR. And now the device IR is sort of packaged using the Clang offload packager. And the packaged device is then fed into the object file. That packs it as a object file, and it can be packaged into the host object file using the -f embed offload object. That's the compilation phase. Let's move on to the linking phase. So the linking phase is what the community uses. It's called the clang-linker-wrapper. And so let's start off with, you have the host object file, which we compiled in the previous slide. And then you also have some device libraries, the SYCL device libraries. So what you do is first thing you do is when you get the host object, now it's a fat object file because it contains both the host code and the device code. The device code is being embedded. So you extract the device code, so which is the device, I think LLVM-IR. And then you pull in all the libraries which are needed to satisfy the requirements of the application, and you do a link. So you use an LLVM link to generate the fully linked device IR, LLVM-IR. And then we do what we call a sycl-post-link. And the sycl-post-link, there are many reasons for this. One of the main reasons is we want to be able to split the files, split the IR, the device LLVM-IR, into multiple LLVM-IR. And an example would be you want to split each kernel itself be contained in a separate image. That's an example I gave. There may be other reasons, like you want to split it based on a file or something. If you have multiple files, you can split it based on a file. And once you split it, now then you invoke the LLVM spurry. So all our backends except, a backend compiler expect spurry code. So we invoke a tool which is called the spurry tool, which converts it into spurry. And at this stage, if the user specified that he wanted the device object file, device image, then we would invoke the AOT compiler at that point. And then once we get the either we get the spurry file or the device image with the invoking the AOT, and those now are wrapped up. What we use is a tool called a clang offload-wrapper. We wrap up these all the multiple images if they have been split. You may not. Sometimes we may not split it, but it will be a single image, and then we invoke the clang offload-wrapper to wrap it into a single file. And now the wrap file is an object file which can be then embedded into the host image. And so now, once we got it wrapped, we got an host image, a .o file with the device image contained in it. And then we invoke the host linker to link in the host code and the device code and to create a single final binary. And so the host code comes directly. Here it's an embedded fat binary. So we have already extracted the device code and processed it. And now we have this part of the host code, which we use then in this final host linker invocation. Okay, so this is the highlight part is what we're trying to change. So that's what we're going to embed, move it into a separate tool called the Clang SYCL linker. And this Clang SYCL linker is going to, process all these things which are highlighted in this darker box. So now let's look at the overall Clang SYCL compiler. So the Clang SYCL compiler, basically, in order to invoke Clang, you would specify what target is. And the target here is spurry. So we say the target is spurry, so the Clang knows use the spurry compilation. And then we say we want to invoke the SYCL link. So we specify the option --SYCL link. And then we may want to pass some linker options to this X linker, where we pass these options to be used during the SYCL linking phase. The Clang, by looking at this --SYCL link, it's going to invoke the Clang SYCL linker to do all the linking which was shown in the previous step. And so we've already put out a PR for this so that we can push it to the community sources. And there's some ongoing discussions, and then some little bit of a debate on whether this tool should be in Clang tool or Link LLVM tool. So we need to work on that one to see how we best can satisfy or where it should live. Okay, so now let's talk about the deviations which we are doing from the existing community scheme. So the first thing is we use LLVM link instead of LTO bitcode linking. Um, the next thing is we link the device libraries at during link time as opposed to during compile time. And the third thing is that we need to pass certain information from the device image to the runtime, especially if you're doing, JIT, right? You want to pass all the optimization flags. And there are other things based on certain aspects in the kernel, we need to pass it to the runtime so it can make use of that and make certain decisions. And then we also have that code splitting, which which we do at the sycl-post-link stage. As I said, we have reasons for doing the code splitting, and I'll explain later on that one. And finally, we use an external tool to convert LLVM IR to SPURV. And in the previous talk, you saw that they're working on this direct code generation to SPURV. Once we have that, we incorporate that and change certain things in this. Okay, so let's talk about the variation one. So we are doing device code linking. The linking is done using LLVM link because we don't have right now a code gen. I said, like I said, right, they're working on it diligently as they presented in the previous talk. So we use LLVM link, and once the SPURV backend is available, we'll switch over to using it with I think thin LTO or LTO. That's a variation. So the second variation is the linking of the device libraries. Again, we do the linking of device libraries using LLVM link at the link time, and we link it, I think, based on a needed basis. And we would, again, if we get the SPURV backend, then we would pull this back into the LTO phase to link in the device libraries. And then the third thing is that we need to send information from the compilation to the image to the runtime. And especially if you're going to do JIT, right, we need to pass these options. We got to honor those options of like you want to use the user specified O0 or something like that. And then we got to honor that flag and pass that information to the runtime. So when you JIT, you use that flag when you're compiling that program with the backend compiler. So what we use a string data map for storing this information. And the next thing is that the SYCL language specifies certain aspects. And so an example would be saying that this kernel uses FP64. And the kernel uses FP32 or something. And so the language specifies that if your hardware doesn't support FP64, then you're supposed to raise an exception. So we need to add these attributes into the kernel, so that kernel, when you're before JITting, you inspect that kernel and then be able to throw this exception if it's not supported on the hardware which you're running. And so we use, again, the string data map to store this. And the way that we store that is we use the structured device image property, where we have a name and a value, and then we have a type, which type can be a UN32 or a byte array. And if it's a byte array, then you have a value size. And so here's another reason why we want to do also a device splitting. So let's say you have two kernels, and one kernel you've written using FP32, and the other one kernel using FP64, and the other one doesn't use FP64. So you be able to select the appropriate kernel depending on which hardware you're running. So if your hardware is supporting FP64, then you would use that. If it doesn't, then you would use the one without the FP64. And so you would need to pass this information. That's why we split the device image into two separate images. One image containing all the ones which require FP30, FP64, and the ones which don't require. And so that you don't try to compile a kernel which requires FP64 when you're running on a GPU which doesn't support it and raise an exception because there's an alternate version available. So this way we can pass this information through the image. And so you can pick up the right image and be able to run the program as opposed to raising an exception if it was a single monolithic image. So that's one of the reasons why we need to split. And also the second reason we want to split is that during JIT time, we don't want to compile all the kernels existing in the thing because you may not use all the kernels in the image. You may use only selected a few kernels. So if you split all this into a separate kernel by itself, then you just load the kernel which is needed and compile only those kernels. So you reduce the JIT over time. And there are also other reasons, like if you want to do, when you're doing AOT, right, by splitting it into separate device images, right, you can invoke the backend compiler in parallel and reduce the compile time. And now the last thing is the variation files. We use an external tool, which is the LLVM SPIRV, to convert the LLVM IR into a SPIRV image. And again, this is now dependent on the code gen being available to directly generate SPIRV code, in which case we can remove the requirement for the this tool. Okay, so the work so far, what we've done is we've submitted RFCs for a couple of them, the top level thing, last year, which I think the RFC is for supporting the full SYCL. It's not just this part, but the full entire SYCL programming model. And then we have added the design for how we go about doing the SYCL offloading kind and SPIRV targets. Now, this similar talk which I'm presenting now was also presented in the Euro 2024 conference. Alexei Sycl presented this, and you can view it if you want on the YouTube link I think provided here. And then the other thing is all these changes I'm talking about. There are two PRs under review. One is to add the IO libraries for SYCL, and the other is to introduce the sycl-linker-wrapper. And would like to acknowledge Joseph for helping us in addressing a lot of issues and getting, I think, widening our knowledge on the new model. And I hope it continues to guide us in that. And then also, I think I want to thank Matt and Chris and Tom for providing feedbacks, and we're hoping to try to get this into the upstream sources. And the next step is we are going to add more PRs to, I think, do the SYCL offloading to the new model. One of them is to run the SYCL finalization step after LLVM will be added inside the sycl wrapper. Then we want to change the clang-linker-wrapper to invoke the clang SYCL linker by invoking clang and then passing the option that SYCL link to invoke the SYCL linker. And then we want to add the offloading logic to the clang-linker-wrapper, the SYCL offloading logic. And then we want to also support, right now we don't have AOT support for any of the targets. We have only a JIT for Intel. We want to add AOT support for Intel, AMD, and NVIDIA. And once SPIRV backend is available, we're going to update that to use the SPIRV and get rid of some of the tools, and also use LTO. And that's it.
Thank you so much for the talk, Ravi. Any questions?
Yeah, thank you. Good talk. So my main question is, you mentioned about using like LTO. Does SPIRV have a defined linking specification for like linking SPIRV with SPIRV? And if it does, then could the ultimate goal be to just make LLD-SYCL or LLD-SPIRV similar to what we do with like the WebAssembly target?
Yeah, that's the plan, but right now we don't have that thing. So we don't have a SYCL linker per se. So we'll have to use the LLVM linker
Okay, thank you.
IP.
Hey, your variation 1, why do you need this tool, like a separate new tool in the first place? Why is that not going to be part of what is upstream? I mean, why? Like basically, you put this overlay thing. Go one back to the one before, when you had this overlay.
Yeah, okay.
That would just basically there was the existing thing, and then you're like, oh, and then we cut out this part here, and then we make it a new tool. Why a new tool?
Joseph can explain that.
So because you were told to make a new tool?
No, because there's already existing similar support for NVIDIA and all that, so we want to follow on those lines.
I see. So existing things.
Existing.
Okay, fair enough.
We're trying to not deviate too much.
What?
They didn't have like a linker executable to fit in with the existing like dev and target toolchain we use. I remember this is because the linker wrapper interface basically tries to use Clang to generate valid images for your GPU target. And the way we do that for like AMD and NVIDIA is dash target, and then we'll invoke stuff like PTX, AS, and NVLink.
Right.
SYCL didn't have one for that, so I told them to make one for it. So that's why it exists. And that's also relates to my question of, or my suggestion that in the future, this is just something called LLD SPIR-V that then does that job for you.
Any other questions? All right, well, another round of applause for Ravi. Thank you.
Thank you.